we just got done doing was finding all the characteristics of graphs of a polynomial. And in chapter 5, we're doing the same thing, but with rational functions. So I did give you a notes handout today because we have some definitions on here, some things to talk about. When I'm looking at a rational function, it's basically just the division of two polynomials. So we're seeing fractions, polynomial on top, polynomial on the bottom. So we're still not going to have any radicals showing up in there or anything like that. And of course, if you have a fraction, we know that the denominator can never be what? 0. So one important concept is the domain. With a polynomial, x could be any number, but with a rational function, it can't, because we know the bottom can't be 0. So the domain is everything except the things that make the bottom 0. In terms of a graph, those are going to be the places where the graph does funny things. And as we go through this chapter, we will be looking at that closer. So first, I just want to practice finding the domain of a rational function. It actually does not matter if things could like factor and cancel. When we're talking about the domain, it's based off the original problem. So when I'm looking at this, I'm looking at the denominator, and I know that it cannot be 0. So x cannot be -5. But how do you think I want you to write your domain? So the denominator can't be 0. We do not care about the top at all. So that means x squared cannot be 4. Square root plus and minus. So x cannot be positive or -2. In the past, I've always told you if it's more than one value x can't be, I will allow you to just list it like that. If you did interval notation, it's everything smaller than -2, everything between -2 and 2, and everything bigger than 2. So we have all 3 different pieces. All right. So if I set that denominator equal to 0, I get x squared cannot be -1. So x cannot be what? Okay. In terms of a graph, can we graph i's? No. So what do you think our domain would be? It can be any real number. We don't care if there's an imaginary that it can't equal. Right, D. My denominator cannot be 0. Does 3 ever equal 0? So what's our domain? Okay. And E. What's the domain going to be? Yeah. If we look at the bottom, can't be 0, so x can't be 1. So our domain is everything else. Negative infinity to 1, union 1 to infinity. Any questions about this? So here is a question for us. Are these equivalent? I mean, first of all, they don't look the same. Why would I even be suggesting that they could be equivalent? Okay. If you were looking at this one, what do you know about x squared minus 1? And what happens there? And we get x plus 1. So do you think they're equivalent? Looks like it. They reduce to the same thing. What is the domain of this one? Right, it's a polynomial, so x can be anything. What is the domain of this one? Okay, why? Denominator can't equal 0. Okay, so do we still think they're the same? Okay, so math-wise, like you've always been taught, you can divide those and it's this equivalent, and that's true. However, if we are going to look at the graph of those, they are not going to be identical because of the domains. So the answer is no. They're different domains. In terms of what the graph would look like, if you're just looking on your graphing calculator, you won't see a difference in the two graphs. They're both going to look like a line. But if you go to like the table feature on your calculator, if you graph this one and you put in 1, it's going to say error for the y. And when we get ready to graph these, what we will actually do is put an open circle on the graph right there, because x can't actually be 1. So these two are identical everywhere except at that one point. But they are not the same because the domains are different. All right. Next feature we need to talk about. Talked about domain. Asymptotes. Those are lines that you are getting close to without touching. There's actually 3 different types: horizontal asymptotes, vertical asymptotes, or oblique. Sometimes oblique is referred to as slant asymptotes, just depending on the textbook you're looking at. So we all know horizontal, that's a horizontal line. Vertical is a vertical line. What do you think oblique would mean? Yeah, any other line is called an oblique. It is possible that a graph could cross over a horizontal or an oblique asymptote in the middle, because they're kind of what the graph does is it goes on to positive and negative infinity. So you can sometimes see a graph cross those, but it will never cross over a vertical asymptote when we're looking at them. All right, so let's look at just the most basic rational function. This one's called the reciprocal function. We're going to kind of treat it like back when we did all of our transformations, we had some parent functions. We're going to look at a couple parent functions today. If we don't know what a graph looks like, how can we get it? XY2 chart, okay. Can you tell me what the domain of this is before I ever graph it? We cannot plug a 0 in there. Okay, so when I'm making my t-chart, I can't put in 0. If I put in 1, 1 over 1 is 1. If I put in 2, 1 over 2, half. If I put in 3, 1 over 3, 1/3. Okay, so this is just getting smaller. Let's go ahead. What if I put in 1/2? What is 1 divided by 1/2? 2. If you flip and multiply, 1 over 1/2 is 2. If I put in a 1/3, 1 over 1/3 is 3. But we can't plug in 0. Can you do 1 divided by something and get 0 for an answer? No. So this is a curve, and it's getting close to 0, but it's not actually hitting it. Okay, if I look at this one, if I put in -1, 1 over -1 is -1. Put in -2, 1 divided by -2 is -1/2. -3 gives us -1/3. If I put in -1/2, we would get -2. If I put in -1/3, -3. So we're getting the same thing. So it's another little curve. It's down here. Okay, make sure when you graph this, I do not want to see, sometimes I have people that graph it like this. What's wrong with that? There's angles. There's no curve to that at all. Is this even a function? No. So it gets hard to draw close to an asymptote, but do your best. This is curved. It's getting closer and closer to the axes, but not touching them. So what's the range of this? Can you look at the graph and tell me what y values we hit? We hit every y value except 0. Vertical asymptote. So asymptotes are lines, so we have to write them accordingly. Vertical line is x equals a number. What vertical line are we getting close to but not touching? 0. Horizontal asymptote. Horizontal lines are y equals 0. Lots of zeros on this. All right, last question. This is bringing back something we haven't talked about in a couple chapters. Even or odd functions. Remember, even is the same thing as symmetric to the y-axis. If I flip this thing over the y-axis, does it overlap itself? No. Odd means symmetric to the origin. Remember, that meant you had to flip over the y and the x. If you flip over both of those, would it overlap itself? Yes. So this is an odd function. All right. Any questions? Let's graph a couple more. So we're going to use transformations. We know what our parent function looks like. It's that 1 over x. What would this plus 1 do to my graph?
Shift it left. I mean right one. Left.
You were right the first time. Add this when you add the x, it goes to the left. Okay. We're going to do just a really rough sketch. So we know this original, and probably I'm going to put my 3 exact points on here. We know 1, 1 would have been on it, and -1, -1. That's what your parent function looks like. So then our transformation, when I move to the left, I'm not only moving these points to the left. Which asymptote would get moved? If you're moving left and right, would that change your vertical asymptote or your horizontal?
Vertical.
The vertical. So my vertical asymptote was right here at 0, so now it's at. We draw asymptotes as dashed lines. Since I didn't move up or down at all, my horizontal one didn't change, so that's just the axis. If you want to draw a dashed line there to kind of remind yourself, we're not crossing that, we're just getting close to it. So my graph looks like this. Same exact thing, but now my vertical asymptote is at -1. Is there any way you could have looked at this equation and known x couldn't be -1? Yeah, that's the domain. So that value that x can't be, your domain value, that's where your vertical asymptote happens. Okay, so what's my domain? What's my range? Alright. Vertical asymptote. What is it? -1. Since it's vertical, we say x equals -1. And the horizontal asymptote is at y0. So you notice the range value? X couldn't be 0, that's your horizontal. Your domain value, it can't be -1, that's your vertical. So your asymptotes are where we see those breaks in our domain range. I want you guys to try the next. What does -2 do? And what would a negative in front do? Over. Okay, so if I move down 2, which asymptote is getting moved? The horizontal one. So it was at 0. You go down 2, it's now at -2. Does the vertical one get moved? Okay. So then we would think if we take our point, if I reflect it over the x, and then go down 2. So it's here, reflect it goes here, down 2. So this curve ends up down here. Okay, this one, I reflect it over the x, it goes up here, then down 2. It's ending at the same spot, but I know it's getting closer to my asymptote. So it looks like this. What's our domain? What's the range? Vertical asymptote. Horizontal asymptote. So moving up and down moves your horizontal asymptote and changes your range. Moving left and right moves your vertical asymptote and changes your domain. Let's look at the reciprocal square function. All right, so let's plug in some points. What is my domain, first of all? Can you tell me? Right, 0 is the thing that makes the bottom equal 0. So if I plug in some points, 1 over 1 squared would be 1. Okay, if I put in 1 over 2 squared, 1/4. Okay, if I did 1 over 3 squared, it's 1/9. So this is getting small really, really fast. What if I put in 1/2? 1/2 squared is 1/4, so 1 over 1/4 is 4. So this is very similar, but it's just a little bit steeper. It's getting bigger faster. The difference we see is when we put in the negatives. What if I put in -1? 1 over -1 squared. What? If I put in -2? +1/4. If I put in -1/2, I get +4. So on the reciprocal square function, because the square makes everything positive, both sides are pointing up. So what range do we have here?
Zero to negative, positive infinity.
We know no negatives, just 0 to
You
infinity.
said negative one, you were done negative.
You think I'm smart? Why can't you throw off of me?
I'm not, I'm just listening to you.
Oh, she thinks
What's
I'm not
the
smart.
vertical asymptote?
What's it called? Yeah.
0, but it has to be x equals, since they're lines, you have to give me the equation. What's the horizontal?
Zero.
Y equals 0, so the asymptotes didn't move. Is this even or odd?
Even.
Even. If you split this over the y-axis, it overlaps itself. So this is
So-
an even.
Will regular reciprocal functions always be like odd or?
Yeah. Well, no. So once you start moving them left, right, up, and down, they're not going to turn out to be even or odd. They'll be neither.
Okay.
Now, if you were just like multiplying it by a number, then it would remain that a reciprocal is odd and the reciprocal square would be even. Alright, let's do one transformation with these. So, I have an x squared. We're just doing a really rough sketch. I'm not going to make you do 3 exact points. We know that both sides give us a positive. So, the graph arrow function is just something like this. What would the -2 do to our graph?
Right.
What asymptote does that move? The x, the vertical one. So we'll have that at +2 now, which we could tell from the equation that on our final answer x could be 2. What does the -4 do?
Bring it down 4.
So my horizontal asymptote is going to end up at and the points right to down 4. So basically whatever's on the denominator will end up being your vertical asymptote. And whatever you're adding or subtracting on the end ends up being your horizontal. What is the domain of this?
Negative infinity to +4.
Domain is x.
Oh, +2.
And then 2 to infinity. Range is our y's, and we're looking, it starts down here at -4, and it's only things above it. So -4 to infinity. I want you guys to try the next one. You're looking at the graph and trying to answer a few questions from that graph. Answer as many of them as you can. Might be helpful to figure out where the asymptotes are and draw those in.